Hello, my name is Mike Buller, and this video explores some of the fundamental principles relating to structural analysis and design. Consider an arched bridge as commonly used in steel construction. They often have 3 pins and are referred to as 3-pinned arches. In determining if this type of structure is statically determinate, we, as per our previous examples, mark up the supports with their unknown reactions. So firstly, the support to the left-hand side has a vertical unknown and a corresponding horizontal unknown. To the opposite support, we also have a vertical unknown and we have a horizontal unknown that is equal in magnitude but opposite in direction to the unknown associated with the opposite side. So note the arrows of the 2 horizontal actions. They effectively cancel each other out. Additionally, we have a pin at the apex. Now this pin on a 3-pinned arch can actually be anywhere. It just so happens that this particular example is near the apex. We can write, as we have done previously where we've had an internal pin within a beam, we can say the sum of the moments at the pin equal 0. If we consider this with our other 3 equations of equilibrium, and as you should know by now, these are the sum of the horizontal forces equals 0, the sum of the vertical forces equals 0, and the sum of the moments equals 0. So if we consider all 4 together, we effectively have 4 equations of equilibrium. We have 4 unknowns, so we can say that this 3-pinned arch is statically determinate. Before we proceed with thinking about how to analyse this and calculate the 4 unknowns, let's give our various unknowns some labels. So we have VA, HA, VB, and HB. We will shortly be considering the moments about A, and one of the things that is going to influence the moment about A is the fact that we have a vertical lever arm between HA and HB. So we have a vertical lever arm of 4 meters. That means that HB is going to generate a moment when we take moments about HA. Hopefully this will become clear in a minute when we actually do the numbers associated with the vertical and horizontal actions. Okay, so we have our statically determinate 3-pinned arch, and we are going to consider our equations of equilibrium. Now we're not going to be able to solve this directly because we're going to have an equation with 2 unknowns in it. So we're going to have to consider how we can solve this simultaneously. So the first step would be to take moments about A. So as you should know by now, we can write the sum of the moments at A equals 0, and as we've done previously, everything going in a clockwise direction we're going to consider positive. So if we consider first of all the 50 kilonewton load to the top of the arch, so we have our pin at A, and then somewhere above that we have our 50 kilonewton load. When we're taking moments, you must remember that the lever arm is the perpendicular distance from the centroid of the action to the point that we're taking moments about. So it's the perpendicular distance between A and the centroid of the 50 kilonewton load, and this is our 50 kilonewtons per meter. So our lever arm, when considering the UD load, is half the width of the arch. It has nothing to do with the vertical height at this stage. You have to remember that taking moments, you consider the lever arm to be the perpendicular distance, so it has nothing to do with the height. So considering the moments at A, we can write plus, and it's positive because the UD load is acting in a clockwise direction about A. So it's trying to rotate in a clockwise direction about A. So it's plus 50 times the width of the arch, which is 24.75 meters, times the lever arm, 24.75 over 2. That's the first part. We also have a vertical reaction at B. So again, if we consider point A, somewhere out here, we have the vertical reaction at B. As I said previously, we have a vertical height of 4 meters, but again, the lever arm is the perpendicular distance. So the lever arm in this case is the full width of the arch. So it's the full width right the way across the arch. That is the lever arm in terms of VB, and that's 24.75 meters. So for VB, that is trying to rotate the whole arch in an anti-clockwise direction about A, so that becomes negative. So we're going to be minus 24.75 VB. The final load we have to consider is HB. HB acts in a horizontal direction. So it's acting horizontally at the same point as VB, so it's at the pin, and as I said earlier, it has a lever arm of 4 meters. Again, it is the perpendicular distance. So the lever arm is this 4 meters here. It's the perpendicular distance, so from the pin at B vertically to the pin at A. So for HB is acting in a clockwise direction. It's trying to rotate the whole frame in a clockwise direction about A, so we can say it's plus 4 HB. And as we know, going back to our equation of equilibrium, all of that equals 0. That is our first equation, and as you can see, we have two unknowns. So we have VB and we have HB, both as unknowns. So obviously we can't solve that directly. What I'm also going to do at this stage, I'm just going to write an expression for firstly the sum of the horizontal forces equals 0. So we are now looking at anything acting horizontally, so that's going to be HA and HB. And if we assume that everything acting from left to right is positive, we would write that plus HA minus HB equals 0. So that's an expression for our second equation of equilibrium. And for our final equation of equilibrium, we can consider the sum of the vertical forces equals 0. And for this, we're going to assume that anything acting vertically up is positive. So we can write plus VA, because we're assuming that is acting up, plus VB, again, we're assuming that is acting vertically upwards, minus the sum of the UD loads. And again, all of that equals 0. We can give this a few numbers. So we've got VA, that is still an unknown, plus VB, again, that is an unknown, minus 50 times 24.75 0.75. That is your UD load across the top of the arch. And that, both of those equal 0 because they have to satisfy our equation of equilibrium. The next step, once we have found our 3 equations of equilibrium and we have an expression for each of them, and as I said earlier on, they all have 2 unknowns, so none of them we can solve directly. The next step is to formulate an expression in the same form, i.e. it has 2 unknowns, the same 2 unknowns as we're using in our moment expression. So we want to formulate an expression that has VB and HB as unknowns, and then we can solve those simultaneously by substitution. We have one more equation that we can now use to formulate our 4th expression, and that is the sum of the moments at the pin equal 0. So if we consider the pin at the apex of the arch, from the pin we consider everything to the right. So we consider our arch that spans to the right of the pin. And we have at the bottom, we also have a pin. To our frame, we add our unknown reactions. So at B, we have the vertical reaction associated with the pin, and we also have the corresponding horizontal action. At the pin, as with our beams, we have a vertical reaction at the pin, and we have a corresponding horizontal reaction at the pin. And the last bit of this free body diagram that we should add are our loads. As you know, when constructing a free body diagram, we should add all the actions. So we have our UD load acting across the top of the arch. And the last bit, as we've done previously, is to add the magnitude of the load and any relevant labels and dimensions. Now we have our free body diagram, we can take moments about the pin. Again, we are going to assume that everything acting in a clockwise direction is positive, everything acting vertically up is positive, and everything acting from left to right is also positive. So we can write first of all the sum of the moments at the pin equal 0. And if we can consider the UD load first, it is acting in a clockwise direction. So the UD load itself is trying to rotate the frame in a clockwise direction about the pin. So we can write plus 50 times 14.5, that's the magnitude of the load, times the distance over which it acts, times the lever arm, 14.5 over 2. That takes care of our UD load. We now have VB. VB is acting vertically upwards, and it is trying to rotate the frame in an anti-clockwise direction about the pin. So it's minus VB times 14.5. And bear in mind what I said earlier on about the lever arm. The lever arm is the perpendicular distance. So in the case of the vertical action at the pin, the perpendicular distance is 14.5 meters. It has nothing to do with the vertical height. And lastly, we can consider HB. And HB is trying to rotate the frame in a clockwise direction about the pin. So we can write plus HB times, again, the perpendicular distance, and this time it's 15 meters. And again, to finish that off, to comply with our equation of equilibrium, the sum of the moments equals 0. And if we simplify that, we can write it as 5256.25. That's the total UD load times its lever arm, minus 14.5 VB plus 15 HB, and that equals 0. And if we go back and look at our original equation for the moment, so this one here, that is in the same form effectively. We have VB and HB as the two unknowns. So we can write our original equation. Let's call that equation 1. And our second moment equation we'll call equation 2. We can simplify equation 1, and that becomes plus 15314.06. That is your UD load, the total UD load times its lever arm, plus 4 HB minus 24.75 VB. And again, that equals 0. And that's just our simplified version of equation 1, so we'll still leave it as equation 1. So we now have two equations in the same form, and we can solve these simultaneously. So by substitution, I'm going to take equation 2 first of all, and I'm going to write equation 2 in terms of HB. So we can write 15 HB equals 14.5 VB minus 5256.25. And we can simplify that, so we get an expression for HB, and HB equals 0.967 VB minus 350.4. And we'll call that equation 3. So we now have two equations in the same form with two unknowns. So we're going to put equation 3 back into equation 1. And that's going to give us 15314.06 plus 4 times, and then this is where equation 3 comes in, 0.967 VB minus 350.4, and then minus 24.75 VB, and that all equals 0. And if we simplify that, we get 13912.46 minus 20.88 VB equals 0. So VB we get as 666.3 kilonewtons. So we've now solved one of our two unknowns, and the rest of the solution becomes fairly simple. Now we have VB, we can resolve everything vertically to give a value for VA. So if we scroll back up a little bit, we wrote earlier on an expression for the sum of the vertical loads. So we can substitute VB back into that and get a value for VA. So if we write out that expression first of all, we have the sum of the vertical loads equals 0. And going back to what we had originally, we had VA plus VB minus 50 times 24.75, and that equals 0. If we substitute VB into that, we get VA plus 666.3 minus 50 times 24.75, and that equals 0. And simplifying that a little bit, we would end up with VA equals 571.2 kilonewtons. Okay, that's resolved everything vertically. We can now think about the horizontal actions. And if we go back up again, we now have a value for VB. So using equation 1, we can substitute our value for VB in there and resolve that to give us HB. So from equation 1, we had 15314.06 plus 4HB minus 24.75 times VB. That all equals 0. So if we now substitute our value of VB in there, we get 15314.06 plus 4HB minus 24.75 times 666.3 equals 0. Again, simplifying that, we end up with a value of HB equals plus 294.2 kilonewtons. Now, if we go back to our original drawing, HB, if we consider the curve of the frame, we had a pin connection down at the bottom, and we assumed that HB was acting from right to left, so we drew an arrow acting from right to left. The reason this is positive is because that assumption is correct. If our calculated value of HB at this stage were negative, that would indicate that HB acted the opposite direction. Please note that the direction of HB that we've calculated, where we have calculated it being positive, that has nothing to do with the global coordinate system. Now the global coordinate system, so for the whole frame, we would have had X in the positive direction that way and Y in the positive direction going vertically up. That would be positive. That is the global coordinate system. So in the local coordinate system, HB is positive, but in the global coordinate system, we have HB acting in a negative direction. So in the global system, HB equals minus 294.2 kilonewtons. As I say, for our calculations, we've been working in a local coordinate system relative to the reaction at B. So a local coordinate system, our calculated value of HB ends up as being positive. So the last part of this calculation is now obviously to work out what the value for HA is. So from equation 2, we have plus HA. We are now thinking in a global coordinate system, so plus HA minus HB, because obviously Mr. Newton said that every action has an equal and opposite reaction, so to be in equilibrium, the force at HA has to be balanced out by the force at HB. So it's HA minus HB equals 0. So we end up with HA minus 294.2 equals 0. That gives us HA equals 294.2 kilonewtons. Again, that infers that our assumption that HA acts from left to right is correct. That in essence completes this particular problem, something that at first glance looks very difficult to solve. All you're doing is simply applying the equations of equilibrium and remembering that the offset of the horizontal force at HB from HA gives a lever arm. Because you have a lever arm, it generates a moment. Therefore, you end up with two unknowns in your first moment expression. You have to develop a second expression with the same unknowns and then solve those simultaneously. I hope you have found this video useful. If you have any comments or suggestions, please do send me an email at the address shown on screen. Thank you for watching.